Limits with infinity. What happens when x gets either really, really big, positive infinity, or a really, really big negative number, negative infinity? So this first one, what happens as x gets really, really big in x squared? Your answer gets really, really big. So we sometimes write our answer to something like this as infinity. As x gets really big, x squared also gets really big. Okay? Some textbooks write does not exist in this situation because technically infinity is not a number. But it is kind of nice to actually say it doesn't exist because it gets really, really big. And this tells us a little bit more that way. What happens as x gets really big and you had negative 3x minus 5?
Negative infinity.
It's going to be negative infinity. Because a really, really big number times negative 3 will make it really big and negative.
Will we still be marked wrong if we said did not exist?
For these ones, I want you to write which infinity it goes to, because what we're telling here, the way this connects to grade 12, in grade 12, here's negative 3x minus 5, right? And what a limit as x goes to infinity is looking at, it's looking at, we called it end behavior. Remember that? How does your graph end? This one ends by going down forever. Going down forever. What does that say to your y values? They're getting bigger and bigger, but negative. So we would say the limit as x goes to infinity for this one is negative infinity. The limit as x goes this way to negative infinity would be positive infinity. So limits to infinity are talking about the end behavior of your graph. So often, first thing you're going to think about is if I put in a huge number, will it get huge or will it get small? In this case, if I put a huge number in and I cube it, it's going to be huge. The next question you're going to ask yourself, will this be negative or will it be positive? And if you cube a negative number, it's going to be negative. This one's going to be negative infinity. If r is bigger than 1, if your exponent is bigger than 1, things are just going to get bigger and bigger and bigger. If your exponents, I forgot announcements. I guess we did not win the chat that we never participate in. We didn't win again. Okay. Yeah. We'll listen to announcements tomorrow. I'm sure it'll be fine. You guys can remind me. I'm usually pretty good, right, about remembering announcements. But sometimes I get excited about everything I want to teach you. And then I'm like, forget about announcements. Why doesn't it work with less than 1? Well, sometimes if you have things like a half, and you do a limit as x goes to negative infinity, well, you can't square root negative numbers. So we get like problems that way at times. So for sure when x is bigger than 1, or when our exponent is bigger than 1, that limit will go to infinity. What happens as n gets really, really big here? It goes to 0. Does it make sense that your end behavior, you have an asymptote? Right, there's an asymptote there. And your graph is approaching that asymptote, we would say that it gets close to 0. Okay? So as n goes to infinity, it's 0. As n goes to negative infinity, it's 0. As n goes to 0, we would say that's undefined because part of it goes up and part of it goes down. Your left side goes down, your right side limit would go up. So that would be definitely someplace where you would say does not exist. What's the limit as n goes to negative infinity of this? Well, you can start breaking things up. You can do this part separate. That's always going to be 5. If you have the number 5, it doesn't matter what n is going to, it's going to be 5. And this part separate. Well, if n gets really, really big, positive or negative, this will get close to 0. 5 minus 0 is equal to 5. So this, anytime this is bigger than 0, the bottom will get really, really big, even if it's slow. And your limit is 0. Find the limit as it exists, or if it exists. What will happen to this if n is really, really, really big? And sometimes you try really big numbers, like you try a million. If I put in a million, it's equal to 1. Then I try a billion, it's equal to 1. I try a trillion, it's equal to 1. So my brain starts to go, I think it's equal to 1. Why am I wrong? Yeah, if I did a billion and 1, then it would be negative 1. If I did any odd number, does it make sense that odd numbers would keep it negative? Even numbers would make it positive? So as you get bigger and bigger, it's not like all of a sudden like, oh, we're tired of the odd numbers. Every number over a quadrillion is even. No, that does not ever hold true. So this one flips between negative 1 and 1 and does not exist. Right? Because it keeps flipping. And that's if we just take whole numbers. What if you did 1,000,000,001 divided by 2? That would involve a square root, which makes it not even possible to do. So sometimes they're not going to exist because they don't get closer and closer to a number. Limit as n goes to infinity of 1/2 to the n. Well, we can think about exponent rules. This is like 1 to the n on the top and 2 to the n on the bottom. What does 1 to the n go to? 1. And 2 to the n goes to huge. I don't know if that's a number. 2 to the n gets bigger and bigger and bigger. So does it make sense that this will be 0? Do you want to see a really weird limit?
No.
Yeah, it's really cool. It's like the coolest limit ever. Check this one out. In your brain, does your brain say 1? You see 1? Because if n is huge, this 1 over n should be 0, right? And then 1 to a huge number, 1 plus 0 should be 1. The last time I checked. And 1 to a huge number should be 1. So everything in our mind here, if we are guessing and checking, says 1. But it's not 1. Because exponents are more powerful than dividing. So this is affecting it more than the 1 over n. You could type this in, like you can plug in 10 and see what it's equal to. You can plug in 100 and see what it's equal to. And you could keep plugging in bigger and bigger numbers, and that's crazy. That's E. That's really weird. But you, yeah, type in 100, you get really close to 2.71828, 1828.
The compound
It is compound interest. Compound interest formula is very similar to this. And do you remember the formula for continuous interest? Continuous growth has E in it. Because if you continually did it as n went to infinity, you get E. Anyways, we're seeing some of the connections between limits and numbers we've done before. If r is between -1 and 1, right, this is another way of saying this. Absolute value of r less than 1 is another way of saying r is between -1 and 1. And if you have a fraction, this is from our geometric sequences, our infinite series with geometric sequences. If your r value is between -1 and 1, then the sum to infinity existed. Well, that's because the limit as n goes to infinity of that goes to 0. Yes?
is it greater, less than or equal to? Because
Oh, no, you're not equal. Thank you for noticing that. I just got a little careless. Just less. Because if it was 1, it would just stay 1. And then it wouldn't go to 0. So, some things you can think about with infinite limits, especially with rational functions, and this goes back to our videos, right? When you were graphing rational functions, if you looked at the degrees, and the degree was bigger on the bottom, you had a horizontal asymptote at 0. That was telling you its end behavior for this one will equal 0. Now we can show some math. I really am happy with you just going equals 0 here. Okay? The mathematics that you can show is you can factor out the highest degree. So if I took the 7 over 2x plus 1, and I notice that x is my biggest degree. If I factor an x out of the top, I'd be left with 7 times 1 over x, or 7 over x. Does that make sense? And if I factor an x out of the bottom, I'd be left with 2 plus, if you take the x out of the 1, would be left with 1 over x. And then these x's would go away. And now what happens when I put in a very, very big number? This would be 0, right? And this would be 2 plus 0. And 0 over 2 would be 0. Although, I'm going to say I'm not going to ask you to show that work. Are you okay with just knowing that the bottom gets really, really big? And if you divide by a huge number, you're going to get next to nothing. Imagine it this way. The 7 on the top. This weekend's my birthday. I'm going to buy 7 birthday cakes. And I don't want anybody in the world to feel bad, so I'm inviting everyone. Everyone can have some cake. The whole world. I have 7 cakes. That's a lot of cake. How much would each person in the world get? Next to nothing. The slivers would have to be so small in the end. That's what's happening here. You're dividing by a huge number. Right? In the end, everybody's going to come. Some people are going to fly from Tokyo, and that's all the cake I'm getting. Flights are super expensive too, because everybody's flying here for my birthday. They're going to be super disappointed. So. Yeah. I am fine with you just saying the answer to this one. Can you see what the answer will be as x gets really, really big? Again, from our video yesterday, look at the highest powers. 4x over 2x. It's going to get really close to 2. If you wanted to factor out the x, you could. You want to see that? Or are you okay with just saying 2? Okay, we're good. So, if the degrees in a polynomial are the same on the top and the same on the bottom, then it's going to go to 0. And in fact, we can do limits to infinity by thinking about these things, even with stuff that we can't do mathematically. Limit. Here, I'll give you one. X goes to infinity. We have to think. What do you think is more powerful? Power of 7. That's pretty powerful. Exponent of x. Also pretty powerful. Which one do you think is more powerful? If you think the x to the 7 is more powerful, then this limit will be does not exist. Because it'll just get bigger and bigger and bigger, or it would be infinity. If you think the 3 to the x is more powerful, then the bottom gets bigger faster, and then your limit would be 0. So if you're unsure, you could plug in 10. 10 to the 7 plus 1 divided by 3 to the 10. Then you could plug in 100. 100 to the 7 plus 1 divided by 3 to the 100. Which one gets bigger faster? The bottom. So this, without doing any kind of real math, the bottom is more powerful. Even if this was a 1.01, which is really close to 1. As x gets really, really big, the bottom will eventually overpower the top. Exponents are more powerful. And so a lot of limits is a little bit of like waving the hands and sort of feeling like, I think this is bigger, so therefore it's 0 because it's bigger on the bottom. Here, these are about the same. The plus 7 and the minus, or the minus 7 and the plus 4 really don't make a difference. We can just look at the biggest degree. Because when x gets huge, it's going to be 4x over 2x. And just equal 2. Okay? Again, we could show our work. Just eyeballing this, what do you think the answer is? You got an x cubed on the top, an x squared on the bottom. Which is more powerful? The top. It's going to be infinity. If you wanted to show your work, you could. Okay, what would it look like to show the work? Well, I would divide everything by an x cubed. If I divide everything by an x cubed, this is what I get everywhere. Which will give me 2 minus 0 plus 0 over 0 minus 0 plus 0, which is 2 divided by 0. Now dividing by 0 is tricky, because if your 0 is positive, it'll go to positive infinity. If your 0 is negative, it would go to negative infinity. In this case, as x gets really big, do you see the top number definitely would be positive, and the bottom number definitely would be positive. So positive over positive will give you infinity. But this is the easier way. Look at the highest powers. Just 2x cubed over x squared. That simplifies to just be 2x. And the limit as x goes to infinity of 2x would be positive infinity that way as well. In the video, they say interesting things happen with square roots. Okay? Because again, the biggest thing on the top is, oh, I don't want one. The biggest thing on the top is the 9x squared. The biggest thing on the bottom is the x. So if we were just doing this mental math-wise, and I just looked at the biggest ones, the biggest one on the top is the 9x squared. The biggest one on the bottom is the x. And the number one mistake that students do is like, oh, I can square root this. And that's just 3x, and it's x. So these cancel out, and I'm just left with 3, and I say my answer is 3, and I get it wrong. Why did I get it wrong? Because technically, the square root of 9x squared is the absolute value of 3x. Especially if x is being negative. Whenever you do a square root, your answer is always positive. So if I square root 9x squared, it's got to be a positive answer. But if x goes to negative infinity, 3x will be negative. So I need to make it positive. Now, can I cancel those x's out? Not really. Not at this point because I have absolute values. So as x goes to negative infinity, 3x will actually be negative 3x. Because it has to be positive. So to make, if I plug in a negative number, to make it positive, I'd have to multiply by a negative. Which, when divided by x, makes this negative 3. So if we look at our highest powers, square roots are tricky. Especially if you're going to negative numbers. Okay? Another technique that we saw in the video yesterday. You can change it to go to positive infinity by making all of your x's negative. Does that make sense? Like if x goes to negative infinity with x's there, I can change it to go to positive infinity if I change all my x's to be negatives. Then I would have the limit as x goes to infinity. Well, this just is 9x squared. And because it's positive numbers, then I can just write 3x without absolute values, because x's are positive anyways. But then I would still have the negative x on the bottom, would still give me negative 3. Limit as x goes to infinity of 1 over x. Well, 1 over infinity would get really, really close to 0. And so sine of 0 gets really, really close to 0. You remember this? What's that equal to? 1. Can you see that that's the same thing? Because if x goes to 0, this goes to 0, this goes to 0. As x goes to infinity, this goes to 0, this goes to 0. Another way of asking that same theorem. Okay, so we can get the same thing asked in a bunch of different ways. And it's us knowing the main thing well and then being able to see where the other things show up that can help us. All right. Limit as x goes to infinity of 3 to the negative x. What does that negative exponent mean? That means that that 3 would be on the bottom. Do you see that this makes the bottom very, very big? Dividing by a very, very big number makes it 0. Limit as x goes to negative infinity. We've got a bunch of things happening here. And the negative makes it interesting as well. We're going to think about different things separately. This, as x goes to negative infinity, right, would be like that, if I change it to infinity, which would make it that. That part will be 0. So I know that part is 0. And what about the rest of it? This part is stuck between -1 and 1. So that means when I'm thinking about this, in my head, this part is 0. Then I'm going to add something between -1 and 1. I'll just write it like, just kind of, I'm going to get some number between -1 and 1 on the top. But then I'm going to be dividing by something huge and positive on the bottom. Does it make sense that in the end, this whole thing will go to 0? Because I'll have some little number on the top divided by a huge number on the bottom. But that's not necessarily easy to see when we analyze the original part. Okay? This one's kind of intriguing. What happens in this situation? Well, my initial brain would look at this and say, well, inside the square root, as x goes to infinity, I really only think about the 9x squared because it's the biggest. And the 9x squared, when I square root it, becomes 3x. So my brain kind of says, I think it should be 3x minus 3x. I think I should get 0. I feel really good about 0. And depending on, like, if you like science better, right? Science is more like, you're close enough. We're not worried about too many decimal places, or, right? So 0 is actually a pretty close answer. The answer is 1/6. But in math, On a multiple choice question, they will have 0 there, they will also have 1/6. You want to just okay.
Right, your calculator.
No, it's not. So what can we do, and what does this look like or remind us of? Sure looks like I have a square root. Maybe I should try the conjugate and see what happens if I try the conjugate. If I try the conjugate and I multiply out the top really nicely, my 9x squareds go away. This doesn't look like anything is getting simplified. But now, I've got an x on the top, a 3x on the bottom, and the square root of 3x squared on the bottom. The idea here, and I'll just do an extra step. If we use the technique that we used at the beginning, but I kind of said sometimes you can ignore it. It sometimes is really nice to do it formally. If you factor out an x, okay? So if I factor out an x on the top, obviously it's going to be x times 1. If I factor out an x on the bottom, how do I do that? How do you take an x out of 9x squared plus x? And I'll do an extra step. I want to take an x out of there. Do you see that that would be like having an x squared inside? And if I take an x squared out of this, I'm going to get 9 plus 1 over x. And then this will equal that's taking the x out of the square root of 9x squared plus x. And taking the x out of 3x will be plus 3. Then these would simplify. And if you take the limit now as x goes to infinity, you see that the 1 over x will be 0. And on the bottom you get 1 over the square root of 9 plus 3, which is 1 over 6. Most limits are straightforward. Some get tricky. I would put this one into the tricky category. The idea of factoring out the biggest power, especially when you're dividing, is very, very useful. All right, we'll do one more and then we'll stop with this and we'll go on to a handout. So I want you to think about this one, come up with an answer. I'm going to hand out I think I handed out 1 2p to this row and 1 extra to this row. So I wonder what you're going to do with that. No. There we go. If you factor out an x, that'd be like factoring out an x squared. Then your x's would cancel. Technically, the square root of x squared is absolute value, but because it's going to positive infinity, both of those would be positive, and they could cancel out. So we get a 1 on the top and a -7 on the bottom. -1, 7. Since we have a fraction, if you think about the biggest one on the top and the biggest one on the bottom, this would work to do this one as well. So I think this is a little bit of an easier one. Now I had a couple people ask me about questions from online with composition of functions. So I just handed out to you a little review on the composition of functions and multiple choice. Now, when I mark, I know that most of you have been working already on the AP Classroom stuff. That's due at 11:30. And I know that most of you have done stuff and gotten things wrong and are now like, is my mark going to be 33% because I got 2 out of 6? I'm going to be generous on this first one. But what I want you to realize when doing those multiple choice questions is AP likes to make multiple choice questions that are tricky and focus on little details. Doing that AP Classroom online, you probably were like, what? On some of the, like, how did I get all of these wrongs? What was the trick I was missing? What happened? So first of all, everybody can, like, it's not going to be that I'm going to drop all of your marks drastically by this. Because you're used to the take-home quizzes where when you get it wrong, you find out from your friend you did it wrong. And you like work together and then get it right. So you're used to getting things right eventually. Okay, but we need to also prepare ourselves, because we're going to write an AP exam, where we need to be on our game because there's going to be those little things that are tricky. One of the little things that is tricky is limits of composition of functions. So this is something that came up online. Probably you got these ones wrong. You're with 99% of the world that gets them wrong the first time, so you should feel good that you're normal. Why are they tricky? Well, let's look at them. The limit as x goes to 1 of f of g of x. Well, as x goes to 1, right, on g of x, that's the second graph, it goes to 3. This is mostly right. It does go to 3. And then as x goes to 3 on f of x, it goes to 0. So as far as choices go, you get 0 here and you feel really good about it because you think you've got it right. But then you do another one and you get it wrong. So there's some intricacies of limits. And if you're ever unsure of a limit, you have to remember that the definition of the limit is that the limit from the left side has to equal the limit from the right side. This one works out perfectly fine, but if I look at the limit as x goes to 1 from the left side of f of g of x, this becomes, well, if I come from the left side, that's this way, this becomes the limit as x goes to 3 from the minus side of f of x. Does that make sense as 2 steps? First, as you go from x equals minus 1, where's minus? Yeah, to 1 from the minus side. Here's 1. If I go from the minus side, I'm getting close to 3, but I'm getting close to 3 from the negative side, from the left side. Because it's going 2.99, 2.999, 2.999. So my next step is saying, well, now the inside is getting 3 from the minus side. And if I go from 3 from the minus side, I go here to 0. If I did, I'm going to change colors to purple here, limit as x goes to 1 from the positive side of f of g of x, it becomes the limit as x goes to 3 from the negative side again. Do you see that as you go from the positive side, you're still coming at 3 from the bottom up. And so it's coming on the purple one from the same side later on, which is still 0. This is still 0. And this one is easy to get wrong because you go to 3, you can go from both sides and go to 0. But we're going to get to some questions here. Like this one. Your initial thought on this one is probably the following. As x gets close to 2, f of x gets close to 2. Then as x gets close to 2 on g of x, it does not exist because the left and the right go to different things. Okay? And you pick does not exist because that's listed there and you get it wrong. And you're like, I did the first one, I got it right. I did the second one, I got it wrong. I thought I knew what I was doing. The answer must be wrong. No. Okay. We're going to do the left side limit here. Right? If a limit exists, then it has to be the same from the left side and the right side. So I'm going to go from 2 from the left side first. And I'd first be on f of x. From the left side, that would be this green arrow. And I would be getting close to 2 from the bottom. So then when I go here to g of x, I would have to be getting close to 2 from the left side. Next to purple. If I get close to 2 from the plus side, I'd start on f of x, I'd be getting close to 2 on the plus side. I'd be going this direction. I'd be getting really close to 2, but still from the bottom. So then on my purple, I would still be on this side, going this way. Which feels wrong, right? You want to go from left and right on the second one as well. But both the green arrow and the purple arrow approach 2 from the bottom up, which is 2 from the left side. So the answer to this is -1. Even though a normal limit as x approaches 2 of just g of x does not exist. Whew. That's a little intricate detail, okay? All of you would have got this wrong on the first time you tried. Lots of you will get it wrong the second time you've tried it now that you've seen the right answer. It's that tricky. Does it make sense? Whenever we do a limit of the whole thing, we have to go from the left and the right. The left arrow is green. If I'm going along my green arrow, I'm getting close to 2, but I'm getting close to 2 from like 1.9, 1.99, 1.999. So I have to get close to 2 from 1.9, 1.9, 1.99, which is the left side. Here on the purple one, as I'm coming from the right, I'm getting close to 2, but I'm getting close to 2 from 1.9, 1.99, 1.999. So on the purple one on the next graph, I have to go from 1.9, 1.9, 1.99. Ooh. I like this, okay? Because there was a whole bunch of people that went, because now you see it, right? Some of you are still like, that's okay. Yeah. We'll color code this. X is getting close to 2 first on g of x. So on g of x coming from the left in blue, getting close to 2. Do you see that you're getting close to 2? You're getting close to 1 from 1.1, 1.01, 1.001. You're coming close to 1 from the right, so you would be on this part going this way. Purple, getting close to 2 from the left side. I would be coming close to 1, but I'd be getting close to 1 from 1.1, 1.01, 1.001. I would still be on this part going this way. Do my blue arrows and my purple arrows approach the same number? They do. This limit exists and is equal to 2. What's really good about these composition functions is it gets us back to the basic idea of a limit. The basic idea from a limit, if a limit exists as it approaches a number, it has to equal the same thing from the left as it does from the right. And that, here's the original, here's me going from the left and the right, but that means on the second graph they both happen to be from the same spot. This one. As I get close to x equals -2 on f of x first. Okay, so first x is going to -2 from the left would be this. It's getting close to -1 from the left side, so then I go from -1, I get close to -1 on the left side, would be going about there. Okay, my purple one, as I get close to -2 from the right, it gets close to -2, but from like -1.9, -1 from the top side or the right side. So now I'm approaching -2. They do not approach the same number. My limit does not exist. F of x. Color code this again. As x goes to -1 from the left, it would go to 3 from the bottom. 3 from the bottom means I'm approaching 3 from the left. My purple arrow, if I approach -1 from the right, I'm still approaching 3 from the bottom. The answer to this one is that my y values, both my final arrows, are approaching -2. So the composition of functions is their way of saying, do you really understand limits? Because the definition of a limit says if it exists at a number, the left side has to equal the right side. But now, and I think drawing the colored arrows really helps you see it, right? If I was traveling originally from the left side, I would be getting close to 3, but from the bottom, so that means I'm getting close to 3 and ending up there. I don't want to, okay, I'm just going to give you the answers to these. You can try them on your own. So 6 I don't want to do, because it's 3. It's boring, in my opinion. Is that our last one?
Yeah.
Oh, I wanted to do, I'm going to make one up for you. Okay? We have time? Yes. Here's my f of x graph. I'm going to put a hole at 2, 3. Okay. And here is my g of x graph. And I want to figure out the limit as x goes to 2 of g of f of x. Okay? If I was going to 2 from the left, I would be on f of x first. I would be going this way. Right? Which means I'm approaching 3 from the bottom. Which means I'm approaching 3 from the left. I would be on this going this way. If I was approaching 2 from the right, now I'm getting closer to 3 from the bottom, so I would be this way. And this one does not exist. They usually ask the other ones that exist why. Because if you have the common mistake of not checking it, you just look at the final one and say it does not exist. And you would get it right with the common mistake. But this shows you when it wouldn't exist.